Hi students, this is a question we will be discussing in this video. This question has been taken from this particular question paper code. Please pause the video and read the question. If you have read the question, let's start the discussion. In this experiment, we will be using three solutions. Solution A is 1 molar acetone, B is 1 molar sulfuric acid, and C is 0.2 molar aqueous iodine. As far as A is concerned, we will be taking 25 ml, B is also 25 ml, but C we will be taking 50 ml. The final volume after mixing will be 100 ml. But there is an order in which the reactants are mixed, because in this reaction B is the catalyst, A and C are the reactants. Now the role of the catalyst, all of you know, that will be speeding up the reaction. So as far as this particular reaction is concerned, we can assume that the moment all the three solutions comes in contact, the reaction will start. First we will be taking solution B, followed by A, and the moment C is mixed, the reaction will start. So let's assume that the order in which we take the solutions are B, followed by A, followed by C. Now this is the reaction. So here, after mixing all the three solutions, the color intensity will be maximum. But as the reaction proceeds, iodine gets consumed, the color of the reaction mixture will fade off. That's what you see in this particular diagram. Now, in order to do the kinetics study, what we will be doing is periodically 10 ml of this reaction mixture will be withdrawn and transferred into excess of sodium bicarbonate using a 10 ml pipette. Now there is a point in using sodium bicarbonate. This is a base. This can react with acid. Remember the sulfuric acid what we had used in the beginning? This excess sodium bicarbonate will react with the sulfuric acid that was used as the catalyst. And because there is excess sodium bicarbonate that is being used, all the sulfuric acid will be completely neutralized out. If the sulfuric acid is getting neutralized off, there is no catalyst to speed the reaction, and this is how the neutralization reaction goes. NaHCO3 reacts with sulfuric acid to produce NaHSO4 plus carbon dioxide and water. This carbon dioxide that is produced will help us to understand that the neutralization process is happening. So once the evolution of carbon dioxide stops, we can conclude that there has been complete neutralization of the sulfuric acid. There is another base which is sodium hydroxide. You might be wondering, we could use sodium hydroxide as an option. No, it will not work. Of course, it is a base, it can react with sulfuric acid. But the problem here is, since sodium hydroxide reacts with iodine, it will affect the experiment. Hence, it cannot be used. So now, let's see what happens further. We have arrested the reaction by adding sodium bicarbonate and neutralizing of the catalyst, that's the sulfuric acid. Now our aim is to find out how much of unreacted iodine is present in the solution. For that, we will be using standard thiosulfate solution that will be reacting with leftover iodine. Into this reaction mixture, sodium thiosulfate will be added from a burette. Initially, since the amount of iodine is maximum, color intensity also will be maximum. As the reaction proceeds, iodine amount gets reduced and the color will fade off to pale yellow color. At this point, we have to add starch. This is the indicator for this titration. Now, starch in presence of iodine will be giving this bluish black color. You can see here, the moment starch has fallen, the color is changing slightly. 1 or 2 drops of starch is added and the conical flask is shaken thoroughly. The complete solution will turn bluish black. This is the color of starch in presence of iodine. After that, the titration will be further carried forward. More amount of sodium thiosulfate will be added drop by drop until in a single drop we get a colorless solution. When the solution turns colorless, we come to the conclusion that complete iodine has been reacted off. Now let's start answering the questions. You can pause the video and read the question. In order to prepare the acetone solution, we'll be using 25 to 250 ml volumetric flask. The next part of the question is concerned about calculation of the mass of propanone used in this reaction. For that, the formula is concentration is equal to number of moles over volume of solution in liters, and the number of moles here I can replace it as mass over molar mass. Molar mass over volume of solution in liters, because number of moles is mass over molar mass. Concentration is 1, that's equal to mass is what we are asked to calculate. We are supposed to calculate mass. Molar mass of acetone is 58.08. Volume of the solution in liters. It has to be in liters. Let's assume that we are using a 100 ml standard flask. 100 ml will be 0.1 liters. So now when we calculate the mass, we get it as 0.1 times 58.08, that is 5.808 grams. So here the mass of propanone is 5.808 grams. Moving on to the next question. Please pause the video and read this question. We had discussed this in the beginning. If you can remember, first the sulfuric acid catalyst is taken. To that the reactants A or C can be added. A followed by C. Let's assume this is the order. Explain your choice. All the three solutions comes in contact, the reaction will start. So we can write the reaction starts when all the solutions are mixed or are present. Moving on to the next question, please pause the video and read the question. We said that during the experiment, 10 ml of the reaction mixture will be withdrawn and added into sodium bicarbonate solution taken in excess, and that will be further titrated with sodium thiosulfate solution in order to find out how much of iodine is left unreacted. That section is discussed here in this question. So which is the apparatus that we will be using to transfer the 10 ml reaction mixture? It is 10 ml pipette. 10 ml or 10 centimeter cube pipette. The next part of the question is suggest 2 reasons for using sodium bicarbonate instead of sodium hydroxide. Sodium bicarbonate neutralizes sulfuric acid producing carbon dioxide gas. So the effervescence produced there helps us to understand that the reaction is happening. Once the effervescence stops, the reaction has been over. Now, the problem with sodium hydroxide is that it reacts with iodine and interferes with the experiment. When the brisk effervescence stops, it indicates complete neutralization of sulfuric acid. Reason 2, NaOH reacts with the reactants the reactants acetone CH3, COCH3, propanone. Acetone is propanone and iodine. So it interferes with our reaction. Let's move forward. Please pause the video and read the question. Here, the first portion, section D1, is asking us to calculate the amount of iodine at the start of the reaction immediately after the solutions have been mixed. 10 ml of the solution from the reaction mixture and transfer it into sodium bicarbonate solution to neutralize out the complete sulfuric acid and arrest the reaction. The amount of iodine present will be the original concentration itself, and in order to do this calculation, the formula we use will be M1V1 is equal to M2V2, where M1V1 is the molarity or concentration and V1 is the volume of one of the solutions. Likewise, M2V2 will be the concentration and volume respectively of the other solution. This is for iodine, aqueous iodine, and let's assume that M2V2, this is for sodium thiosulfate. M1 will be molarity of aqueous iodine. We are assuming that the concentration is remaining the same as the original solution because we have transferred, we have taken out immediately after all the three has been mixed. So concentration will be 0.2 molar. We are withdrawing out 10 ml of the solution using a 10 ml pipette. So volume of aqueous iodine taken will be 10 ml. We are using 0.1 molar sodium thiosulfate. So this value will be 0.1 and this is unknown to us. So when we calculate this, we will be getting V2 is equal to 20 ml, or here the volume of sodium thiosulfate used is going to be 20 centimeter cube. Now the next part of the question, the indicator used was starch and the color change, if you can recollect, in the previous section of the video we had shown what was happening. There we had seen that immediately after the addition of starch, the solution was turning bluish black and at the end point it was becoming colorless. So the color change will be from bluish black to colorless. Black to colorless. What are the two variables that must be recorded in this experiment? In this experiment, as time passes by, the color of the solution will be fading away. As amount of iodine gets consumed, the color intensity will be getting reduced. So, one of the variables here is time, and the next variable here, it's not the amount of iodine, of course that is a reactant. The next variable is sodium thiosulfate, which we use for titrating and finding out the amount of iodine that is left unreacted. If there is more iodine or initially in the reaction mixture, the amount of iodine will be maximum. So when we withdraw the sample, initially lot of thiosulfate will be used in titration. Maximum amount of thiosulfate will be consumed in titration in the beginning since maximum amount of iodine is present. As the reaction proceeds, iodine amount gets decreased. So the volume of sodium thiosulfate that is being used also gets reduced. So the two variables in this reaction are, one is time, its unit will be in seconds, and the other is volume of thiosulfate, sodium thiosulfate. So that will be in centimeter cube. State one other variable that must be controlled. A variable that has to be controlled during the course of the reaction is temperature, because when temperature changes, the rate of reaction also will be changing. Here is the next question. Please pause the video and read the question. So here in this question they are asking us to draw a graph for first order reaction. So in this graph, the y-axis will be concentration of iodine. Let's assume y-axis is concentration of iodine and x-axis is time. This being a first order reaction, we will be getting a curve like this. The curve should be having a negative slope like this. This is not the shape of the curve that should be drawn. It is having a downward slope because the amount of iodine decreases as time passes by. Please pause the video. I hope you have read the question. Here, the question is asking us to prove that the reaction is first order with respect to iodine. So, in order to prove that the reaction is first order with respect to iodine, it can be proved based on the half-life. Now, how to prove it based on the half-life? Here, I have taken a rough graph just to show you how half-life will be used to determine the order of the reaction. It's obtained by plotting concentration against time. So, initial concentration is 1 molar. That's the original concentration. As far as the first half-life is concerned, it is the time taken for 1 molar to become half the amount. Half the amount of 1 molar is 0.5 molar. This is 0.5 molar on the curve. And when I'm extending it to the x-axis, this is the time what I get. So it is 1 second. The first t half is 1 second. Now, as far as the next t half is concerned, that will be the time taken for 0.5 molar. This time it is not 1 molar, it is 0.5 molar. Time taken for 0.5 molar of the solution to become half its amount, 0.25. So, here is the 0.25, extending it to the curve, this meets here. Extending it downwards, we get 2 seconds. Now, this gap is 1 second, this gap is also 1 second. Let's see how much is the next half-life. 0.25 has to become half its amount. Half the amount of 0.25 is 0.125. So, somewhere here we have 0.125. It meets the curve here. Dropping it downwards, it meets at point 3. Again, the spacing is 1 second. So, if a reaction is first order, the curve will be like this and we have to get equal spacing for the half-lives. Going back to the previous curve what we have drawn, we also should be getting a curve like that. The best option to do that would be, rather than simply drawing a line somewhere, in order to prove that, what is to be done is, you can put equal spacing here. So 1, 2, 3, let's mark equal spacing here. And here also we need to have equal spacing like that. Okay, let's start from the bottom. 1, 2, 3, 4, 5, 6, 7 and 8. Okay, it's been given that we are using 0.2 molar iodine solution. So let's mark 0.2 here. Here we will be having 0.1. For the sake of simplicity of the calculation, I am using 10, 20, 30, 40, etc. So now we have to get equal spacing. Initial amount is 0.2. Half the amount of 0.2 would be 0.1. Corresponding to this 10 here. I am taking a point here. Next, we have to have half the amount of 0.1. Half the amount of 0.1 is 0.05. In order to have equal spacing, rather than putting it somewhere, this gap is 10. So the next gap also has to be 10 itself. Half of 0.1 is 0.05. See where 0.05 will be meeting 20. So somewhere here. Half of 0.05 would be 0.025. Again, I have to maintain equal spacing. So it will be 30, somewhere here. You have to join all the points and I have to extend it. So now back to this question. How could the graph be used to prove the order of the reaction with respect to iodine as first order? In order to answer this question, we can prove that 2 or 3 half-lives are the same. So let's go with the first half-life, T half 1, that will be equal to, the first T half is the time taken for 0.2 molar solution to get reduced to 0.1. For that, the first half-life is 10. 0.1 molar to get reduced to 0.5. So here also it is 20 minus 10, that is the second T half is 20 minus 10, this is also 10 seconds. For the third half-life, it would be the time taken for 0.5 to become half of it. So 0.5 to become half of it. This is also 10 seconds. It's 30 minus 20. For the third half-life, it would be 30 minus 20. Third half-life would be 30 minus 20. This is also 10 seconds. Moving to the last question, you can pause the video and read the question. Please read the question carefully. It's asking whether temperature will affect the order of the reaction with respect to iodine. The temperature will not affect the order of the reaction. It affects only the rate of the reaction, not the order of the reaction. So the half-life will be still the same if the temperature is changed. Temperature has no effect on the order of the reaction. Order of the reaction. Order of the reaction. And the half-life remains constant. That's all for now. Thank you.